What if I told you a broke 18-year-old kid from Tennessee, working alone in his garage with nothing but some steel tubing, a welder, and sheer stubborn refusal to accept the status quo, invented something so effective that professional racers with $20,000 worth of suspension technology were getting absolutely embarrassed at the drag strip? We're talking about 1.32 60-foot times. The kind of violent, snap-your-neck launches that were supposed to be reserved for purpose-built race cars with tubular chassis and exotic suspension setups. And this kid's entire invention costs $55. $55. Let that sit with you for a second. This is Motorsport Heritage, and I spend way too much time thinking about the moments in racing history where a single idea, born not in some corporate research facility or professional race shop, but in a regular person's garage, completely rewrote the rulebook. If you're someone who loves the engineering side of drag racing and wants to understand how a teenager's backyard invention became one of the most important suspension innovations in motorsport history, make sure to hit the subscribe button and give this video a thumbs up if this helps you out. So here's the thing. It's 1975. You're standing at a drag strip somewhere in Tennessee. The air is absolutely thick with tire smoke, the sweet chemical bite of racing fuel, and that unmistakable electric tension you only get when serious machinery is about to be pointed at the horizon and set loose. In one lane, there's a racer with a full-blown purpose-built drag car, tubular chassis, professional 4-link rear suspension, coilovers, the whole package. This guy probably has 20 grand invested in his rear suspension alone. He's got the look of someone who knows exactly what he's built and exactly how fast it is. In the other lane, there's a beat-up Chevelle. And here's where things get interesting, because if you look quickly, this car looks almost stock. The leaf springs are still hanging under the back end, right where the factory put them. But if you look a little closer, you'll notice something. There are two simple parallel bars running from the axle housing forward to the frame. They look almost primitive. Clean, sure, but basic. Unpretentious in the way that things sometimes look before they change everything. The Christmas tree counts down. Both cars stage. The lights drop. And something that should be completely impossible happens. That beat-up Chevelle with the leaf springs and the $55 homemade contraption underneath it plants its rear tires with the same absolute violence as the purpose-built race car beside it. Both cars rocket forward with virtually identical ferocity. The guy with the $20,000 4-link suspension cannot believe what he just witnessed. He got his doors blown off by a teenager with welded steel tubes. Now, you might be thinking, okay, that sounds cool, but how is that actually possible? How does something so cheap and simple compete with sophisticated, expensive engineering? And that's exactly the question we're going to answer today. Because the story of how ladder bars were invented, how they worked, why they were so devastatingly effective, and how they completely democratized drag racing performance is one of the most compelling stories in all of motorsport. This isn't just a story about suspension technology. This is a story about ingenuity, about physics, about the moment one young person's refusal to accept conventional wisdom permanently changed an entire sport. To really understand why this invention was so revolutionary, we need to go back to what drag racing actually looked like for the average guy in the early 1970s. Because here's what most people don't realize. If you had a leaf spring car and wanted to race it seriously back then, you basically had three options, and they all had serious problems. Option 1 was slapper bars. These were crude devices that bolted to the front spring eye and extended back under the axle. The theory was simple enough. When you launched hard, the axle would rotate under the torque, the slapper bar would hit a rubber snubber, and this would theoretically plant the rear tires. In practice, they worked with about as much consistency as a weather forecast in tornado season. Sometimes they'd hook beautifully. Sometimes they wouldn't engage at all. Sometimes they'd engage at the wrong moment and upset the car mid-launch. You genuinely never knew which version you'd get until you were already heading down the track at speed. Option 2 was bolt-on traction bars. These clamped directly to the leaf spring itself and were supposed to prevent what's called spring wrap-up, which we'll get into in detail in a moment. The fundamental problem with traction bars was that in solving one problem, they created several new ones. By essentially turning your leaf spring into a rigid bar, they eliminated the spring's ability to actually function as a suspension component. Every bump, every seam in the track surface, every tiny imperfection in the racing surface would send a shock directly into the chassis with nothing to absorb it. Your lap time suffered. Your car became harder to drive. And over time, the constant stress would actually crack your springs, leaving you stranded with a broken car and a lighter wallet. Option 3 was the nuclear option. And this is where the real money came in. You tear out the entire rear suspension and convert to a 4-link setup. This meant cutting off the spring perches, welding in new mounting brackets, fabricating or purchasing an entire 4-link kit, installing coilover shocks, and essentially re-engineering everything behind the rear seat. You were looking at thousands of dollars in parts alone before you even thought about the labor involved. And once you made that commitment, your street car wasn't really a street car anymore. Those 4-link setups were brilliant on the racetrack, but on the street, they were absolutely miserable. Every expansion joint felt like a sledgehammer. Every rough patch of road became an adventure in survival. The established racing wisdom said these were your only choices. The professional racers and the chassis companies had everyone convinced that serious traction required complex geometry, expensive components, and effectively turning your car into a dedicated race machine. There was no middle ground. Except, of course, there was. Here's where a teenager's understanding of basic physics outsmarted an entire industry. Because while the professional chassis builders were selling complexity and the racing establishment was preaching expensive solutions, an 18-year-old kid in a Tennessee garage was staring at his leaf spring car and thinking about something much more fundamental. He wasn't thinking about 4-links or instant centers or anti-squat percentages. He was thinking about why his car wouldn't hook the same way twice. And that laser focus on the actual problem, rather than the conventional solutions everybody else was selling, is exactly what led to one of the most elegant engineering breakthroughs in drag racing history. See, this teenager understood something that the established racing community seemed to have completely overlooked in their rush toward complexity. The problem with leaf springs under hard acceleration wasn't the springs themselves. The springs were doing exactly what springs are supposed to do. The problem was a specific, identifiable, and actually quite simple mechanical phenomenon called spring wrap-up. And once you truly understood spring wrap-up, once you could see it clearly in your mind, the solution became almost obvious. Here's how spring wrap-up works. When you mash the throttle in a rear-wheel drive car, the engine sends torque through the drive shaft to the differential. Inside the differential, the pinion gear meshes with the ring gear and tries to rotate around it. This rotational force, this torque reaction, wants to rotate the entire axle housing. Now in a car with a 4-link or a torque arm suspension, there are dedicated links specifically designed to control this rotational force and transfer it cleanly to the chassis. But in a leaf spring car, the leaf springs are being asked to do everything simultaneously. They're supporting the car's weight, providing ride compliance, locating the axle laterally, and now also trying to resist this powerful rotational force. And that's simply too many jobs for one component to handle gracefully. What happens is this. The front section of the leaf spring, the portion forward of the axle, tries to straighten under the rotational force. The rear section of the spring, behind the axle, tries to curve downward. The whole spring starts to deform into an S shape. The more power you make, the more dramatic this deformation becomes. And here's the really insidious part. The spring stores this energy as it deforms, like winding up a rubber band. Then, unpredictably, it releases that stored energy all at once. Sometimes that energy release plants the tires into the track. Sometimes it lifts the tires off the track. Sometimes it creates wheel hop, that violent, rapid bouncing that sounds like a jackhammer and does approximately the same amount of damage. It was, as our young inventor correctly identified, a fundamentally unpredictable and uncontrollable situation. Now look. The conventional solutions all tried to address this problem by adding rigidity. Slapper bars added a mechanical stop to limit rotation. Traction bars tried to prevent the spring from deforming at all. Forelinks eliminated the spring's role in controlling rotation entirely. Each approach was essentially saying the same thing. The spring is the problem, so either fight it or replace it. But here's what most people don't realize. Fighting the spring created inconsistency. Replacing it cost thousands of dollars. Neither approach was actually optimal. Our Tennessee teenager looked at this situation and arrived at a completely different conclusion. What if, instead of fighting the spring or replacing it, you simply separated the jobs? What if you let the leaf spring continue doing what it was genuinely good at, which was supporting the car's weight and providing ride quality, while adding a completely separate, dedicated system whose only job was controlling axle rotation? Division of labor. Simple, elegant, and, as it turned out, devastatingly effective. The solution he came up with was almost disarmingly simple. 2 parallel bars, running from mounting points on the axle housing forward to mounting points on the frame. Each bar would be connected at both ends with rod ends, which are essentially heavy-duty pivoting ball joints. This arrangement would allow the bars to pivot vertically, meaning the suspension could still move up and down freely over bumps and road imperfections. But crucially, the bars could not allow any rotational movement of the axle housing. The moment the axle tried to rotate under acceleration, those bars would immediately transfer that rotational force directly to the chassis. No wrap-up, no stored energy, no unpredictable release, just immediate, consistent, controlled force transfer from the axle to the car. This is where it gets really interesting, because what our young inventor was creating, whether he fully realized it in these technical terms or not, was a system that fixed something called the instant center of the suspension. The instant center is a theoretical point in space around which the suspension rotates when viewed from the side of the car. Think of it like the fulcrum of a lever. The position of this instant center has enormous influence over how the car behaves during acceleration. Get it in the right location and the car squats slightly on launch, transferring weight to the rear tires and maximizing traction. Get it wrong, and the car either launches with the front end sky high in an uncontrolled wheelie, or it sits flat and can't get the rear tires to bite consistently. Professional 4-link suspensions were designed with the ability to adjust the instant center, but this adjustability was simultaneously their greatest strength and their most significant weakness. To use those adjustments effectively, you needed a deep understanding of suspension geometry, considerable experience with your specific car, and frankly, the time and resources to experiment systematically. Get any of it wrong and your expensive 4-link suspension was actually producing worse results than a stock setup. The complexity that was supposed to be an advantage became a liability for anyone without the expertise to navigate it properly. Ladder bars, by contrast, had a fixed geometry. You mounted them according to some basic guidelines that had been established through experimentation. Keep the front mounting point roughly 2 inches higher than the rear. Make the bars as long as practical for your specific application. Make sure they clear all surrounding components through the full range of suspension travel. That was essentially the complete installation guide. No complex calculations, no specialized knowledge required, no expensive trial and error with geometry adjustments. You followed those basic principles, bolted the bars in, and they worked. Every single time. The construction itself was almost laughably straightforward. 2 pieces of steel tubing, typically around 2 inches in diameter. 4 rod ends to provide the pivoting action at each end of each bar. Some steel plate brackets to mount to the axle housing, usually just simple U-shaped pieces that welded directly to the axle tubes. Frame mounting points that could be as basic as flat tabs welded to the frame rails. That was the complete bill of materials. In 1975, if you sourced quality rod ends and decent steel tubing, your total material cost was approximately $55. If you were willing to go a little cheaper on components, you could get there for $35. Any person with basic welding skills could fabricate a set of ladder bars in an afternoon. You didn't need a professional race shop. You didn't need specialized tooling beyond a welder, a drill, and standard hand tools. You didn't need an engineering degree or years of suspension tuning experience. You needed some steel, some rod ends, a welder, and a tape measure. The barrier to entry was essentially nothing, and the performance on the other side of that barrier was absolutely stunning. The first time our Tennessee teenager strapped his homemade creation under his car and pointed it at the drag strip, the results surprised even him. The rear tires bit into the asphalt with an authority and immediacy that he simply hadn't experienced before. The car launched straight, level, and hard. No drama, no wheel hop, no unpredictable energy release from wound-up springs. Just immediate, violent forward acceleration. But the part that really mattered to a bracket racer, the part that meant the difference between winning and losing, wasn't just the raw speed of any single pass. It was what happened on the next pass, and the one after that, and the one after that. Because the car did exactly the same thing every single time. The consistency was unlike anything he'd experienced. The 60-foot times validated everything. Those numbers told the complete story of what ladder bars could do. Street cars with decent traction might run 2.0 to 2.2 seconds 60-foot times. Really well-sorted street machines might dip into the high 1.9s. Professional door-slammer race cars with sophisticated four-link suspensions and racing slicks would typically run in the 1.3 to 1.4 second range. This kid's leaf spring car with its $55 welded tube contraption was pulling 1.32 60-foot times, matching professional race cars, on leaf springs, for $55. Word spread through the Tennessee racing community like fire through dry grass, and the professional racing establishment was about to have a very uncomfortable conversation with itself. Because when racers started showing up at the track, laughing at those simple parallel bars hanging under leaf spring cars, and then watching those same cars cut 1.3 60-foot times, something fundamental shifted in how people thought about performance. The laughter stopped very quickly. The questions started almost immediately, and the answers those questions produced would reshape drag racing for the next 5 decades and counting. The pattern at the track was remarkably consistent. Experienced racers would walk through the pits, spot the ladder bars, and smirk. They'd make comments about primitive technology, about how you couldn't expect real performance from leaf springs regardless of what you bolted underneath them. They'd explain, with the confidence of people who'd invested serious money in their own setups, exactly why what they were looking at couldn't possibly work, as well as a proper 4-link conversion. Then the cars would stage. The lights would drop. And the time slips would come back with numbers that made absolutely no sense according to everything those experienced racers thought they knew. Here's the thing about drag racing. The time slip doesn't care about your opinions. It doesn't care about conventional wisdom or established theory or how much money you spent. The numbers on that little piece of paper are the only argument that matters. And the numbers coming off ladder bar-equipped leaf spring cars were making a very loud, very clear argument that nobody with an expensive 4-link setup particularly wanted to hear. Now, you might be thinking, okay, but surely the professional racers and the chassis builders had good reasons for dismissing this. Surely there was something about the ladder bar design that made it inferior in ways that weren't immediately obvious from the 60-foot times. And look, that's a completely reasonable thing to wonder. The established racing community wasn't stupid. These were people who'd spent years developing their understanding of suspension geometry, who'd invested enormous resources in figuring out what worked and what didn't. They had legitimate expertise. The problem wasn't their knowledge. The problem was their assumption that complexity was inherently superior to simplicity. Professional 4-link suspensions were theoretically superior to ladder bars in almost every measurable geometric sense. They offered multiple adjustment points that could be used to dial in precise anti-squat percentages for any specific application. They could be tuned for different track conditions, different tire compounds, different weather situations. A properly set up four-link, tuned by someone who truly understood what they were doing, could extract slightly more performance than a ladder bar setup in the same car. The mathematics supported this. The engineering was sound. In theory, the four-link should win every time. But here's what most people don't realize about the gap between theoretical performance and real-world results. That gap is enormous. And the size of that gap is directly proportional to the complexity of the system you're trying to optimize. A four-link suspension has multiple adjustment points. Each of those adjustment points interacts with all the others in ways that aren't always intuitive. Moving one adjustment changes the effect of every other adjustment simultaneously. To truly optimize a four-link setup, you needed a systematic approach, considerable experience, reliable data collection, and the patience to work through the variables methodically. Most racers, even serious ones, didn't have all of those things, which meant most four-link setups were running somewhere between mediocre and pretty good, rather than at their true potential. Ladder bars had essentially one geometry. You installed them correctly, which wasn't complicated, and they produced very good results. Not theoretically perfect results. Not the absolute maximum that physics would allow under ideal conditions. But very good, very consistent results that most four-link setups in the hands of most real-world racers simply couldn't match in practice. The consistency was particularly devastating to the four-link argument. Because in bracket racing, where the entire game is running the same elapsed time repeatedly, consistent good results will beat inconsistent great results every single time. The chassis builders were the last to come around, and honestly, you can understand why. These were businesses built on selling complexity. A ladder bar kit cost maybe $60 or $70 in parts plus a few hours of labor if you had someone else build it. A four-link conversion was a multi-thousand-dollar project that required substantial fabrication work and generated serious revenue. The financial incentive to dismiss ladder bars was enormous, and so for a while that's exactly what the professional chassis shops did. They explained why ladder bars were inferior, why the geometry was compromised, why serious racers needed proper four-link setups. They weren't entirely wrong about the theoretical arguments, but they were ignoring the practical reality that was playing out at drag strips across the country every single weekend. The street racing scene adopted ladder bars even faster than the organized bracket racing community. And this makes complete sense when you think about it. Street racers weren't working within a rulebook that specified suspension configurations. They didn't have to worry about class eligibility or technical inspection. They just wanted their cars to launch hard and launch consistently. And they wanted it without spending money they didn't have or destroying the drivability of cars they needed to drive every day. Ladder bars checked every single one of those boxes simultaneously. This is where it gets really interesting from an automotive culture perspective. Because what ladder bars enabled was something genuinely new in American car culture. Before ladder bars, the serious performance world was effectively divided into two categories. You had street cars that were fun but limited in their performance potential. And you had dedicated race cars that were fast but essentially undrivable on public roads. The compromise between those two worlds was always uncomfortable and usually expensive. Ladder bars started erasing that line. Suddenly a car could drive to work Monday through Friday, stop at the gas station, navigate traffic, carry passengers, and then go to the track on Saturday and launch with the authority of a purpose-built race machine. The street strip car, as a concept, existed before ladder bars, but ladder bars made it genuinely viable for ordinary people with ordinary budgets. The 60-foot times that ladder bar cars were producing on the street weren't just impressive in isolation. They were impressive relative to what those same cars had been capable of before. A Chevelle that previously struggled to run consistent 2-second 60-foot times might suddenly be cutting 1.45s after a weekend installation of $55 worth of steel tubing. That's not a marginal improvement. That's a transformation. The car felt completely different to drive at launch. the tires hooked instead of spinning or hopping. The acceleration was immediate and linear instead of violent and unpredictable. Drivers who'd been fighting their cars for years suddenly found themselves working with them instead. The physics underlying this transformation are worth understanding in some detail, because they reveal just how well conceived the basic ladder bar design actually was. When you launch a leaf spring car hard without any traction-enhancing device, several forces are competing simultaneously and chaotically. The torque reaction is trying to rotate the axle. The weight transfer is trying to compress the springs. The springs are simultaneously trying to maintain their natural shape while being distorted by both the weight transfer and the torque reaction. The interaction between all these forces creates a dynamic system that's genuinely difficult to predict or control. Every tiny variation in throttle application, track surface, temperature, tire pressure, or a dozen other variables produces a different outcome. Ladder bars imposed order on this chaos by separating the forces. The leaf springs continued handling weight support and vertical compliance. The ladder bars took exclusive responsibility for controlling the rotational forces. Each component was now doing one job instead of several, and each component was therefore able to do its job properly. The leaf springs could respond to weight transfer and track irregularities naturally, providing the compliance that made the car manageable. The ladder bars controlled axle rotation with absolute consistency, ensuring that the torque reaction was always transferred to the chassis in exactly the same way regardless of other variables. The mounting geometry that our Tennessee teenager arrived at through intuition and experimentation has since been validated extensively by computer modeling and engineering analysis. Bars mounted with the front pivot point approximately 2 inches higher than the rear, at a length of roughly 32 to 36 inches, creates an instant center that sits near the height of the car's center of gravity and slightly forward of the axle centerline. This specific geometry produces a mild squat on acceleration, transferring weight rearward to increase tire loading exactly when and how you want it. It's not accidental that this geometry works so well. It's the product of intuitive physical understanding translating perfectly into mechanical design. The bracket racing community felt the impact of ladder bars most profoundly and most quickly. Bracket racing, remember, rewards consistency above all else. A car that runs 10.5 every single pass will beat a car that runs 10.21 pass and 10.8 the next. Because bracket racing is about predicting and matching your own performance, not just going as fast as possible. Ladder bars delivered consistency that leaf spring cars had never previously been capable of. Cars that had previously frustrated their drivers by running wildly different elapsed times from one pass to the next were suddenly clicking off run after run within hundredths of a second of each other. The 60-foot variation, which had been the primary source of elapsed time inconsistency for leaf spring cars, essentially disappeared. By the late 1970s, even the professional racing establishment couldn't ignore what was happening, and the aftermarket industry was about to change forever. Because when consistent real-world results keep contradicting established theory week after week, month after month, at drag strips across the entire country, eventually even the most stubborn institutional resistance has to give way to reality. The professional chassis builders and racing companies faced a choice. Acknowledge what ladder bars were accomplishing and adapt, or watch their authority and their market share erode as racers voted with their wallets and their time slips. Most of them, to their credit, eventually chose adaptation. And the industry that emerged from that adaptation looks remarkably like the performance aftermarket we know today. The first major aftermarket companies to offer production ladder bar kits did so almost apologetically. There was a sense in the early marketing materials that these companies were offering ladder bars despite their reservations about the design, rather than because they genuinely believed in it. The kits were presented as budget solutions, affordable alternatives for racers who couldn't justify the investment in a proper 4-link conversion. The implicit message was clear. This is the cheap option. It works reasonably well, but if you were serious, you'd do the 4-link. What those early marketing positions completely failed to anticipate was how quickly the time slips would make that framing irrelevant. Companies like Lakewood, Competition Engineering, and Calvert Racing were among the first to bring production ladder bar kits to market. And here's what's interesting about what happened when they did. The kits sold immediately and in enormous numbers. Not because racers were settling for a budget option, but because racers had watched ladder bar cars perform and understood that budget and performance weren't actually in conflict here. The demand wasn't coming from people who wanted ladder bars because they couldn't afford better. It was coming from people who wanted ladder bars because they'd seen what ladder bars could do. That's a fundamentally different market dynamic, and it caught the established companies somewhat off guard. The production versions of ladder bars refined the basic concept in several important ways without fundamentally altering the design. Adjustable front mounting points were introduced, allowing racers to experiment with instant center positioning for their specific applications. Polyurethane bushings were offered as an alternative to rod ends for street-driven cars, providing slightly more compliance and significantly better durability under daily driving conditions. Detailed installation instructions made the process accessible to people who were competent with basic tools but didn't necessarily have fabrication experience. Heavier wall tubing and better quality hardware improved durability for high-power applications. But through all these refinements, the core design remained exactly what that Tennessee teenager had figured out in his garage. Two parallel bars, pivoting at both ends, controlling axle rotation while allowing vertical suspension movement. The professional racing establishment's formal acknowledgement came through the rulebooks. When the National Hot Rod Association and the International Hot Rod Association updated their class regulations to specifically address ladder bars, it represented official recognition that this technology was legitimate, significant, and here to stay. The rule writers had to grapple with where ladder bars fit within existing class structures. For classes that required retention of the stock suspension type, ladder bars were generally permitted because they worked with the existing leaf springs rather than replacing them. This was an important distinction that opened up entire segments of organized racing to the technology. Cars that competed in stock suspension classes could now run ladder bars and access performance that previously required a full suspension conversion and a move to a different class. Here's what most people don't realize about the ripple effects of that regulatory acknowledgement. It didn't just validate ladder bars as a racing technology. It validated the entire philosophy behind them. It said, officially and in writing, that innovative solutions developed outside the professional racing establishment deserved recognition and accommodation. That a design born in a teenager's garage was worthy of a place in the rulebooks alongside equipment that had been developed by professional engineers with substantial resources. That performance didn't require pedigree. That's a significant cultural statement, even if it was delivered in the dry language of technical regulations. The elapsed times that ladder bar cars were posting through the late 1970s and into the 1980s continued to push boundaries that had previously seemed unreachable for leaf spring vehicles. Leaf spring cars with ladder bars were running deep into the 10-second range, then the 9s, then the high 8s in particularly well-developed applications. These weren't specialized, lightly modified bracket cars. These were serious performance machines that happened to retain their leaf spring suspension because ladder bars made that suspension genuinely competitive. The old argument that you needed a four-link to run in the serious numbers was being refuted run after run, track after track across every region of the country where drag racing happened. The Calvert racing bars, introduced in the early 1980s, represented one of the most significant evolutions of the ladder bar concept. Caltracs, as they became known, used a single bar per side with a spring-loaded mechanism that preloaded the suspension in a specific way before launch. They weren't pure ladder bars in the traditional sense, but they operated on the same fundamental principle of controlling axle rotation while allowing vertical suspension movement. They added a layer of tunability to the basic concept, allowing racers to adjust the preload to suit different conditions and power levels. The success of Caltracs demonstrated that the underlying ladder bar philosophy had room to evolve and improve while retaining its essential simplicity and accessibility. The influence of ladder bars extended well beyond drag racing, and this is a dimension of the story that often gets overlooked. Circle track racers discovered that controlling axle wrap under hard acceleration out of corners could meaningfully improve their exit speed and consistency. Off-road racers found that ladder bars prevented the axle wrap that could upset a vehicle's trajectory when climbing steep obstacles or accelerating hard over rough terrain. Towing applications benefited from improved stability under the heavy loads that could otherwise induce spring wrap-up in leaf spring-equipped trucks. Ladder bars turned out to be solving a problem that existed anywhere leaf springs and significant torque coexisted, which is a remarkably broad range of applications. The financial mathematics of the ladder bar revolution deserve serious attention because they illustrate the scale of what actually happened in the performance market. Consider a conservative estimate. In the decade between 1975 and 1985, let's say 50,000 leaf spring drag cars across the country switched to ladder bars instead of converting to 4-link setups. A 4-link conversion in that era cost somewhere between $2,000 and $5,000 depending on the application and who did the work. Ladder bars cost between $55 in raw materials for a fabricated set and perhaps $150 for a quality production kit. The savings per car ranged from roughly $2,000 to $5,000. Multiply that across 50,000 cars and you're talking about somewhere between $100 million and $250 million that stayed in racers' pockets rather than going to chassis shops. That money went into engines, tires, fuel, entry fees, and simply racing more often. The economic democratization was staggering. This is where it gets really interesting from a broader industry perspective. Because that money didn't disappear from the performance aftermarket. It redistributed. Racers who'd saved thousands on suspension spent those savings on other performance components. The engine builders, the carburetor specialists, the ignition companies, the tire manufacturers all benefited from the money that ladder bars freed up from suspension budgets. The overall performance market grew partly because ladder bars made serious performance accessible to people who'd previously been priced out. New participants entered the sport. Existing participants could afford to do more. The rising tide lifted all boats, even the boats belonging to the chassis builders who'd initially resisted the ladder bar concept. The street performance culture that exploded through the 1980s owed a significant and underappreciated debt to ladder bars. The muscle car revival of that decade, the explosion of interest in street strip machines, the culture of dual-purpose performance vehicles that could genuinely perform at the track without sacrificing street usability, all of this was enabled in important ways by the ladder bar's ability to deliver race car launches without race car compromises. A generation of young people who'd grown up watching ladder bar cars perform at their local tracks entered the hobby with a fundamentally different expectation about what was possible on a realistic budget. They didn't accept that serious performance required serious money because they'd seen the evidence with their own eyes that it didn't have to. The professional chassis builders who survived the ladder bar revolution and built successful businesses through the 1980s and beyond were the ones who figured out how to embrace, rather than resist, the technology. They developed premium ladder bar kits with better materials and tighter tolerances. They produced installation guides and technical support resources. They innovated within the basic design, finding ways to add value through quality and refinement rather than complexity. The companies that clung to the argument that 4-links were categorically superior to ladder bars lost market share steadily, and some lost their businesses entirely. The market had spoken clearly, and the message was that performance and accessibility were both values that racers cared about deeply. Modern computer modeling and finite element analysis have done something remarkable to the reputation of that original Tennessee garage design. Engineers with advanced degrees, sophisticated software, and access to resources that would have been unimaginable in 1975 have examined the ladder bar geometry in exhaustive detail. And what they've consistently found is that the basic geometry arrived at through intuition and experimentation half a century ago is remarkably close to optimal for the vast majority of drag racing applications. Not perfect, not the absolute theoretical maximum in every situation, but genuinely, impressively close to what the math says it should be. For a design developed by an 18-year-old with a welder and a tape measure, that's an extraordinary validation. Here's the legacy that most racing histories get completely wrong about ladder bars, and why their story matters far beyond the drag strip. Because most accounts of this technology focus exclusively on the mechanical innovation, on the geometry, and the physics, and the elapsed times. And while all of that is genuinely fascinating, it misses the deeper significance of what actually happened when a teenager with $55 worth of steel tubing outsmarted an entire industry. The real story of ladder bars is a story about what becomes possible when someone refuses to accept that expensive is synonymous with better, that complexity is synonymous with performance, and that innovation belongs exclusively to people with resources and credentials. That story is worth telling carefully, because it contains lessons that extend far beyond anything that happens between the Christmas tree and the finish line. This is where it gets really interesting from a broader industry perspective, because that money didn't disappear from the performance aftermarket. It redistributed. Racers who'd saved thousands on suspension spent those savings on other performance components. The engine builders, the carburetor specialists, the ignition companies, the tire manufacturers all benefited from the money that ladder bars freed up from suspension budgets. The overall performance market grew partly because ladder bars made serious performance accessible to people who'd previously been priced out. New participants entered the sport. Existing participants could afford to do more. The rising tide lifted all boats, even the boats belonging to the chassis builders who'd initially resisted the ladder bar concept. The street performance culture that exploded through the 1980s owed a significant and underappreciated debt to ladder bars. The muscle car revival of that decade, the explosion of interest in street strip machines, the culture of dual-purpose performance vehicles that could genuinely perform at the track without sacrificing street usability, all of this was enabled in important ways by the ladder bar's ability to deliver race car launches without race car compromises. A generation of young people who'd grown up watching ladder bar cars perform at their local tracks entered the hobby with a fundamentally different expectation about what was possible on a realistic budget. They didn't accept that serious performance required serious money because they'd seen the evidence with their own eyes that it didn't have to. The professional chassis builders who survived the ladder bar revolution and built successful businesses through the 1980s and beyond were the ones who figured out how to embrace rather than resist the technology. They developed premium ladder bar kits with better materials and tighter tolerances. They produced installation guides and technical support resources. They innovated within the basic design, finding ways to add value through quality and refinement rather than complexity. The companies that clung to the argument that four links were categorically superior to ladder bars lost market share steadily, and some lost their businesses entirely. The market had spoken clearly, and the message was that performance and accessibility were both values that racers cared about deeply. Modern computer modeling and finite element analysis have done something remarkable to the reputation of that original Tennessee garage design. Engineers with advanced degrees, sophisticated software, and access to resources that would have been unimaginable in 1975 have examined the ladder bar geometry in exhaustive detail. And what they've consistently found is that the basic geometry arrived at through intuition and experimentation half a century ago is remarkably close to optimal for the vast majority of drag racing applications. Not perfect, not the absolute theoretical maximum in every situation, but genuinely, impressively close to what the math says it should be. For a design developed by an 18-year-old with a welder and a tape measure, that's an extraordinary validation. Here's the legacy that most racing histories get completely wrong about ladder bars, and why their story matters far beyond the drag strip. Because most accounts of this technology focus exclusively on the mechanical innovation, on the geometry, and the physics, and the elapsed times. And while all of that is genuinely fascinating, it misses the deeper significance of what actually happened when a teenager with $55 worth of steel tubing outsmarted an entire industry. The real story of ladder bars is a story about what becomes possible when someone refuses to accept that expensive is synonymous with better, that complexity is synonymous with performance, and that innovation belongs exclusively to people with resources and credentials. That story is worth telling carefully, because it contains lessons that extend far beyond anything that happens between the Christmas tree and the finish line. The tracks themselves noticed. Bracket racing fields grew through the late 1970s and 1980s, partly because more cars were genuinely competitive. When the performance gap between a well-funded car and a budget build narrows significantly, more people are willing to pay their entry fee and line up to race. The racing is more exciting when the outcome is less predetermined by equipment budgets. The competitive ecosystem becomes healthier when talent and preparation matter more than spending power. Ladder bars contributed meaningfully to all of this, not through any grand social vision, but simply by making consistent competitive performance available to anyone willing to spend $55 and an afternoon in the garage. This is where it gets really interesting when you consider how the ladder bar story maps onto broader patterns of innovation throughout motorsport history. The most transformative developments in racing have rarely come from the best-funded teams or the most established organizations. They've come from people operating at the margins, working with limited resources, forced by necessity to find solutions that expensive development budgets would never have discovered, because expensive development budgets don't have the same incentive to question fundamental assumptions. When you have plenty of money, you build a better four-link. When you don't have plenty of money, you ask whether a four-link is actually necessary. That question, asked seriously and answered through experimentation, produces ladder bars. The pattern repeats throughout racing history. The underdog with limited resources who asks the question that well-funded establishments take for granted, and discovers that the answer challenges everything the establishment has built its authority around. It happened with aerodynamics in Formula One, where a small team's willingness to question conventional body shapes led to insights that the major manufacturers had overlooked. It happened in endurance racing with tire strategy and fuel economy. It happened in stock car racing with chassis setup philosophies that originated in small independent shops before being adopted by factory-backed teams. And it happened in drag racing with a teenager's welded steel tubes that made professional suspension engineers deeply uncomfortable. The modern relevance of ladder bars is itself a remarkable statement about the quality of the original design. We're now approaching 50 years since those first homemade ladder bars went under that Tennessee Chevelle. In those 5 decades, engine technology has been transformed almost beyond recognition. Carburation gave way to fuel injection, which gave way to computer-controlled sequential injection with individual cylinder tuning. Transmissions evolved from 3-speed manuals to sophisticated automatic units with computer-controlled shift points and torque converter lockup strategies. Tire technology advanced through multiple generations of compound chemistry and construction techniques. Data acquisition went from a guy with a stopwatch to onboard computers logging dozens of parameters hundreds of times per second. And through all of that transformation, ladder bars remained essentially unchanged. The same 2 parallel bars, pivoting at both ends, controlling axle rotation while allowing vertical suspension movement, doing exactly what they did in 1975. Not because nobody tried to improve on them. Multiple companies introduced devices marketed as ladder bar replacements or improvements. Most disappeared within a few years, unable to match the combination of effectiveness, simplicity, and affordability that had made ladder bars ubiquitous. The market kept returning to the original solution because the original solution was, in its fundamental conception, correct? Walk through the pits at any drag strip today, from a small bracket racing event at a regional track to a major national event, and you will see ladder bars. Under cars making 500 horsepower and cars making 2,000. Under vehicles that run 14-second quarter miles and vehicles that run 7-second quarter miles. Under pristine professional builds and under rough around-the-edges budget machines. The technology has proven itself across an extraordinary range of applications and power levels that the original designer could never have anticipated. Those simple welded tubes have proven capable of handling forces that would have seemed fantastical in 1975, because the fundamental physics they exploit don't change regardless of how much power you put through the system. The name of that Tennessee teenager has been largely lost to history. Most accounts of ladder bar origins are frustratingly vague about the specific individual responsible for the first application. The first time someone looked at those parallel bars and understood what they could accomplish. And there's something both sad and somehow appropriate about that anonymity. Sad because genuine innovation deserves recognition, and the person who figured this out deserved to have their name attached to one of drag racing's most significant developments. Appropriate because the whole point of the ladder bar story is that the innovation came from outside the credentialed establishment, from someone whose identity was irrelevant to the validity of their insight. The idea was right regardless of who had it. The time slips didn't care about the inventor's age or budget or credentials. They just reported what actually happened. Here's the thing about legacies in motorsport. The ones that matter most aren't always the most celebrated. The famous engine builders, the legendary chassis constructors, the celebrated tuners, these people get their recognition. Books get written about them. Documentaries get made. Their names become shorthand for excellence in their fields. But the teenager in Tennessee who figured out how to control axle rotation with 2 pieces of steel tubing changed more lives in practical terms than most of the celebrated names in the sport. He gave hundreds of thousands of racers access to performance they couldn't otherwise have afforded. He changed the culture of drag racing by demonstrating that the game wasn't exclusively for people with deep pockets. He proved that understanding matters more than resources, that clear thinking about a specific problem is worth more than expensive solutions to the wrong problem. Every pass down a drag strip made by a ladder bar-equipped car is a continuation of that original insight. Every racer who bolts on a set of ladder bars instead of spending thousands on a 4-link conversion is benefiting from what one young person figured out through careful observation and clear thinking. Every bracket racer who clicks off consistent run after consistent run, confident that their car will launch the same way every single time, owes something to that $55 invention. The technology has launched millions of passes. It has enabled countless racing careers that financial barriers would otherwise have prevented. It has made the sport richer, more competitive, and more accessible than it would have been without it. The next time you're at a drag strip and you see those simple parallel bars hanging under a car in the staging lanes, take a moment to really look at them. Look at how straightforward they are. Look at how obviously they do exactly one job with no pretension toward doing anything more than that one job perfectly. And remember that you're looking at one of the most democratizing innovations in the history of motorsport. Remember that those basic tubes came from a garage, not a research facility. From necessity, not from a development budget. From a teenager who refused to accept that going fast required going broke. Remember that sometimes the most important engineering insights aren't the most complex ones. Sometimes they're the ones that look at a complicated problem and find the simple truth hiding inside it. And remember that the next great innovation in any field might be sitting right now in someone's garage, taking shape at the hands of someone who simply refuses to accept that things have to be done the expensive way. Because if history has taught us anything, it's that those are exactly the people we should be paying attention to.